Welcome. In part 1, we touched upon the topic of recursion. In this section, we'll try to understand the concept of something known as lambda in recursive least filters, and this lambda is also known as forgetting factor. So let's revisit our scalar filter as shown in the diagram. So we have a filter which has a weight Wn, and Xn is the input to the filter, Yn is the output of the filter, and we have a desired signal, a copy of it. So when we subtract the output of the filter from the desired signal, we get an error. And the attempt is that we must tweak this coefficient of the filter Wn so that the output of this filter becomes as close as possible to this desired signal, thus reducing this error to 0. So let's start. Here Xn is the input to the filter. Wn is the coefficient or weight. Since we are considering the scalar case, we have only one coefficient. And then we have the output of the filter, Yn. We have Dn, which is the desired signal. And En is the error. So now the whole attempt here is to figure out how to calculate Wn, optimal Wn, which results in the least amount of error, preferably 0. So this filter can then be expressed as follows. Our output is nothing but a combination, a dot product between the weight and the input, and then it has some error. Essentially, we can rewrite this equation, the error equation, as follows. Yn minus Wn Xn. So this becomes our first equation. Let's say equation 1. And now the attempt is that this error must get reduced by manipulating this weight. So for that we define a cost function, and that cost function we will call it JW. This cost function basically implements nothing but sum of squares errors. So what I mean by that is that JW is nothing but we have error, we square it, and then we sum it from, say, so this is what is the sum of squares error. And actually if we expand this in form of series, this is how it will look. So it is E1 square plus E2 square plus E3 square plus so on and so forth till En square. Now what we want to do is that we do not want to treat all these errors from E1 to E9, En equally. Let's say this is the current time and this is the past. Essentially time is going in this direction. So we want to weigh these past errors with a number which is very small. Basically we are trying to forget this past error as much as possible, and we want to give higher weightage to the current error. How we can do this is by this. Let's say there's a coefficient called lambda 1, which when gets multiplied by the first error term reduces it, and then there's another one, lambda 2, E2 square, and so on and so forth till we reach lambda and En square. And the condition here is that lambda 1 must be smaller than lambda 2, must be smaller than lambda 3, so on and so forth until we reach lambda n. So we have to then find a function which formulates this series. And there are multiple ways of doing it. Firstly, let's try to graph it. So let's say I have a time axis here, and I have this some function of lambda which must implement decrease to increase kind of scenario. So one way of doing it is that we can just simply take a linear function like this. So this is past, this is present, and as you can see in the past we are attaching a very low value to this point, and in the present we are attaching a very high value to the function. Now this is one way of doing it. The other way of doing it is that instead of using a linear function, we can use exponential function too, something like this, or something like this, or we can actually make something even steeper like this. So let's see what all functions implement this family of functions. So let's say Let's say there's a lambda. We define lambda in such a manner that lambda is always between 0 and 1. It is greater than 1, it is greater than 0, but lesser than or equal to 1. If we have such a lambda, if we have such a number, for example, let's say lambda is equal to 0.1, we can manipulate its power. Let's say we raise this lambda to a power of z, where z is varying from 0 to n. And let's say n for this purpose is 10, so from 0 to 10. So what will happen here is that since I have lambda is 0.1, and let me start with 10, then 9, 8, so on and so forth until I reach 0. So what do I get here? Here I get a number 10 raised to the power minus 10, which is a very small number. And again, this is a very small number, 10 raised to the power minus 9, 10 raised to the power minus 8, so on and so forth. Eventually, I will get 1. So my numbers are increasing. This function is increasing in this manner. So essentially, I have to manipulate the power of lambda, and I will be able to implement a function like this as long as lambda is less than equal to 1 and greater than 0. Now, how this can be implemented? So we have defined a cost function, and now we will do something like this. We have a k which is varying from, it can vary from 0, but for the practical purposes, let's say from 1 to n. And then I define lambda, which is nothing but n minus k. And then we have this term ek square. So what will happen, let's say n is equal to 10, and k is varying from 1 to n. So let's see what happens to n minus k. N minus k in the first go will be 20 minus 1, that is 19, then 20 minus 2, that is 18, 20 minus 3, that is 17, and so on and so forth until it is 20 minus 20, which is 0. So these are the powers that are being applied to this lambda function, and hence this lambda will act like this. From a very small number, it will go up to 1. So why are we doing this? Basically, what we are trying to do is that we have an error whose characteristic is changing. For example, it is mixed with a noise which is having statistical properties which are varying over a period of time, essentially a non-stationary noise. So if we forget the distant past value of the noise, or give lower weightage to this noise and give more weightage to the current value of this noise, then our filter is actually tracking the changes in the statistical properties of that noise. What are those statistical properties? It can be mean, it can be variance. This over a period of time is changing. So we should not get stuck in the past. We should start to forget the past and start to concentrate more on the current errors, so that we are able to keep track of changes in the statistical properties of the noise that we are dealing with. So essentially, this lambda 1 E1 square plus lambda 2 E2 square, so on and so forth until we reach lambda is equal to 0 En square, where this becomes 1, and this is a very small number. As I said, let's say lambda was 1, this is raised to the power 19. So this component of the error will be given very small weightage, slightly bigger, until we give full weightage to the current error. So that's what we are trying to do here. And eventually this whole cost function becomes so this is what forgetting factor is all about. And the purpose of defining this cost function in such a manner is that noise that we are dealing with, or the filter is exposed to, is non-stationary, meaning the statistical properties of the noise are varying over a period of time. They're a function of time. So let's see how this entire function is executed in Python. So in this code, we will implement the forgetting factor. I have imported some libraries, NumPy and Matplotlib, and let's start. So I've defined a factor, lambda factor, which is 0.95, which is in accordance with our rule, that is lambda should be greater than 0 and less than or equal to 1. For the purpose of this example, we'll take n is equal to 100. That means there are 100 error terms in the series. And we will define time axis, which is going from 0 seconds to 1 second, having n time points, which are linearly spaced. And then we are going to define an error, a random error, by this expression, which is basically suggesting that it's a Gaussian error with 0 mean and 0.06 as its standard deviation. And we will have 100 terms in this error. Basically, this is simulating the difference between the filter output and the desired signal. And then we'll initialize two series to save our lambdas and our cost function. So what we are doing here is we are looping through all the values from k is equal to 0 to n, and we are calculating the lambda. If you remember, lambda was nothing but lambda raised to the power n minus k, and then we are going to save this value of lambda in this array, which we have initialized here with all zeros. And then we'll calculate our cost function. Our cost function was this part, the lambda raised to the power n minus k, which is captured by this, and the square of the error. So error is coming from here. And then we are going to save this cost function, every value of it, in this series that we have initialized here. And then we are going to plot error and both these time series. Let me run the code. And as you can see, so the first plot has time as its x-axis, and on the y-axis we have the function outputs. So what we are seeing here is we have implemented this lambda function, which is depicted by this orange line. It's an exponential function, as you can see clearly. And then we have this error, unweighted error, which I said that it was a Gaussian error with zero mean and some standard deviation. So this blue line is indicating that error. It is going in both the directions, negative and positive. And then we implement the square of this error. So once we square this error, this negative part will disappear, which is what is being shown by this green line. And this green line is actually a multiplication between this lambda function and the positive value or squared values of the error. So with lambda is equal to 0.95, what we see here is that these are all the past values, and these are all this is the present value of the error. So what has happened, if you see this green line closely, the past errors, in spite of being very large, they have been given very little weightage, and they have been actually forgotten. So the more we are in past, the more this function is trying to forget those errors. And as we keep moving, you see this green line starts to increase in amplitude, which is lesser than the actual noise, because we have weighted it with this exponential function. But it is remembering the recent errors more vividly with more weightage than what it was doing in the past. So that's the function, that's the purpose of this forgetting function. The recent error terms are given more weightage. You can see this in better detail in this plot number 2, which is again the same thing. The blue is the original noise terms or the error terms. And what you see in orange color is after we have squared this noise and multiplied it with the lambda function, then you see that all these past errors have very low amplitude or very low values because we have forgotten them. And then the current values of this error are being remembered and are being weighted with the lambda function. So if you see this this orange peak here, it is almost as close as to the original noise, signifying that this is giving full weightage to the present value of the noise. Now what I have done is that instead of using just one value of lambda, I'm going to use 3 values of lambda varying from 0.9 to 0.99. The idea is to show the effect of the value selected for the lambda on the performance of the forgetting factor. So we will consider these 3 different forgetting factors, and rest is the code remains just the same, and I've done plotting. So after executing the code, this is what you see. So there are 3 lambdas, 0.9, 0.95 and 0.99. So the lower the value of lambda, as you can see here, a large amount of past values are disregarded. So you see this red line, which is the cost function. So from this point onwards till almost from the start, all the error values have been forgotten, and only the present value has been given the most weightage. And that has happened because the lambda has a very small value, 0.9. Let's see if we increase it to 0.95. So you see that in comparison to this red line, which has forgotten all the past values till here, you see that it remembers, it is going in past more in depth in comparison to the previous one. And when we come to 0.99, you see that a large number of past values have been remembered by the function, by the cost function. So it is taking into consideration, it is allowing the filter to go back in the past and consider the values of the errors which has happened in the past. So this is the impact of lambda on the cost function.